In 6.7, we'll be talking about exponential and logarithmic models. The characteristics of the exponential function model is that an exponential function with that form has the following characteristics. It's a one-to-one function. It has a horizontal asymptote at y equals 0. The domain is always going to be from negative infinity to positive infinity. The range goes from 0 to infinity. It doesn't have an x-intercept because it doesn't cross the y-axis, the x-axis. The y-intercept is 0 and the initial value. It's increasing if k is greater than 0, which is the first graph, and it's decreasing if k is less than 0, which is the second graph on the right. So in example number 1, we're going to be graphing exponential growth. So a population of bacteria doubles every hour. If the culture started with 10 bacteria, graph the population as a function of time. Now, when an amount grows at a fixed percent per unit time, the growth is exponential. To find the initial, we use the fact that the initial value of A is the amount at time 0. So at time 0, there's 10 bacteria, so A subscript 0 is going to be equal to 10. Now, to find the value of K, we're going to use the fact that after 1 hour, when T is equal to the 1, the population doubles from 10 to 20. So the formula is derived as follows. So for step number 1, we're going to write down the given information. We know T is going to equal 1, we know that Y is going to equal 20, and we know the initial is 10. So we're going to use our exponential function model here, which is Y is equal to the initial value of A, e to the kt. So we know that Y is 20, we know that A, or the initial, is 10, and we know that time t is 1, so it's 1k. So we're going to solve for the value of k by first dividing both sides by 10. So we get 2, which is equal to e to the k. And then to solve for k, we're going to take the natural log of both sides. So we get the natural log of 2, which is equal to k. Or just rewriting it, writing k on the left side and natural log of 2 on the right side. So now we know that k is going to equal the natural log of 2. And then we can substitute it back into our growth model. So our growth model is then going to be y equal to 10 e to the power of the natural log of 2 times t, because that's what the value of k is. Or we can say y is equal to 10 times 2 to the power of t. And so here is our graph. So again, it's a increasing function. Now, the population of bacteria after 10 hours is 10,240. We would describe this amount as being of the order of magnitude 10 to the 4th power. The population of bacteria after 20 hours is 10,485,760, which is of the order of magnitude 10 to the 7. So we could say that the population has increased by 3 orders of magnitude in 10 hours.